What if everything you thought you knew about the universe was just the tip of the iceberg? What if the rules of time and space, the very foundation of reality as we understand it, could bend, twist, and even break? This isn't the plot of a science fiction novel, it's the real, mind-bending world of space-time distortion. From the crushing gravity of black holes to the eerie stretching of time near massive objects, the universe is full of phenomena that defy logic and challenge our understanding of existence. In this video, we'll uncover 20 astonishing aspects of space-time distortion that seem like they've been plucked straight from the realm of imagination. Get ready to explore concepts that will stretch your mind, from wormholes to gravitational waves, and discover how these cosmic oddities hold the key to unlocking the universe's greatest mysteries. This isn't just a journey through space, it's a journey through the very fabric of reality itself. Imagine standing at the edge of a cosmic abyss, a place so powerful that it swallows light itself. This is the realm of black holes, where gravity reaches unimaginable extremes, warping the very fabric of space and time. At the heart of every black hole lies the event horizon, a boundary that acts like a one-way door. Once something crosses this threshold, there's no turning back, not even for light. It's as if the universe itself has drawn a line, marking the ultimate point of no return. But what makes black holes truly fascinating isn't just their destructive power. It's how they reveal the strange and twisted nature of space-time. Near the event horizon, time doesn't behave as we know it. If you could somehow hover just outside this boundary, you'd witness time slowing down dramatically, as if the universe were hitting the pause button. This phenomenon, known as gravitational time dilation, was predicted by Einstein's theory of general relativity and has been observed in the way black holes interact with their surroundings. It's a stark reminder that time isn't constant, it's flexible, bending and stretching under the influence of immense gravity. In recent years, black holes have moved from theoretical curiosities to tangible objects of study. The historic first image of a black hole, captured by the Event Horizon Telescope in 2019, was a groundbreaking moment. That haunting, fiery ring of light, the accretion disk swirling around the event horizon, gave us a glimpse into the heart of one of these cosmic giants. It confirmed decades of scientific predictions and opened new doors for understanding how space-time behaves under extreme conditions. But black holes aren't just destructive forces, they're also cosmic laboratories. They allow scientists to test the limits of physics, probing the nature of space-time in ways that would be impossible anywhere else. From the way they distort light to the mind-bending effects they have on time, black holes challenge our understanding of reality itself. They remind us that the universe is far stranger and more complex than we often imagine, and that there's still so much to discover. What if the universe had secret tunnels, hidden pathways that could transport you across unimaginable distances in the blink of an eye? This isn't just the stuff of science fiction. It's the intriguing idea behind wormholes, one of the most fascinating concepts in theoretical physics. Often described as cosmic shortcuts, wormholes are hypothetical structures that could bend the fabric of space-time, creating a bridge between two distant points in the universe. Picture folding a piece of paper so that two far apart points touch. That's essentially how a wormhole might work, allowing for travel that defies the usual constraints of distance and time. The idea of wormholes traces back to the early 20th century, when physicists like Albert Einstein and Nathan Rosen explored solutions to the equations of general relativity. These equations suggested that space-time could be warped in such a way that it forms a tunnel, or Einstein-Rosen bridge, connecting two separate regions. But here's the catch. While the math allows for the existence of wormholes, making them stable and traversable is another story entirely. Most theoretical models show that these tunnels would collapse almost instantly unless some form of exotic matter, material with negative energy, could be used to prop them open. This is where science fiction and reality collide, because such exotic matter has never been observed in nature. Despite the challenges, wormholes remain a tantalizing concept. If they could be stabilized, they might offer a way to traverse vast cosmic distances without breaking the speed of light. Imagine traveling from one galaxy to another in mere moments, bypassing the billions of light years that would normally separate them. Even more mind-bending is the possibility that wormholes could enable time travel. By connecting not just points in space but also moments in time, they might allow for journeys into the past or future. But this raises some perplexing paradoxes. What happens if you travel back in time and alter events? Would you create a new timeline, or would the universe somehow prevent such contradictions? These paradoxes highlight the complexities and limitations of wormholes. While they're a thrilling idea, they also remind us that the universe often has ways of enforcing its own rules. For now, wormholes remain firmly in the realm of theory, a fascinating puzzle that challenges our understanding of space, time, and the very nature of reality. Whether they're the ultimate cosmic shortcuts or just a mathematical curiosity, one thing is certain: wormholes keep us dreaming of the possibilities hidden within the fabric of the universe. Now let's shift our focus to something equally extraordinary: gravitational waves. Picture the universe as a vast, calm lake. When a stone is tossed into the water, ripples spread outward, disturbing the surface. Gravitational waves are like those ripples, but instead of water, they travel through the fabric of space-time itself. These waves are generated by some of the most violent and energetic events in the cosmos, like the collision of black holes or the merging of neutron stars. In 2015, scientists made history by detecting these elusive ripples for the very first time, confirming a prediction Albert Einstein made 100 years earlier. The discovery was made possible by the Laser Interferometer Gravitational Wave Observatory, or LIGO, an engineering marvel designed to detect the tiniest distortions in space-time. LIGO works by splitting a laser beam into two perpendicular paths, each traveling down a 2.5-mile-long tunnel. When a gravitational wave passes through, it subtly stretches and compresses space-time, causing the lengths of these tunnels to change by an almost unimaginably small amount, less than 1/10,000th the width of a proton. This minuscule shift is enough for LIGO-sensitive instruments to pick up, revealing the presence of a wave that has traveled across billions of light years to reach us. The implications of this discovery are staggering. Gravitational waves don't just confirm Einstein's theory, they give us an entirely new way to observe the universe. Unlike light, which can be blocked or distorted by dust and gas, gravitational waves pass through everything unimpeded. This means we can listen to cosmic events that would otherwise remain hidden, like the final moments of two black holes spiraling into each other. These collisions release an immense amount of energy, shaking the very fabric of space-time and sending waves rippling across the cosmos. Through gravitational waves, we've gained a front-row seat to some of the most dramatic events in the universe. But the story doesn't end there. Gravitational wave astronomy is still in its infancy, and each new detection brings fresh insights. By studying these waves, scientists can map the distribution of black holes and neutron stars, uncovering the hidden structure of the universe. They can also test the limits of general relativity, probing whether Einstein's equations hold up under the most extreme conditions. In some ways, gravitational waves are like cosmic messengers, carrying information about the universe's most mysterious phenomena directly to us. This discovery has revolutionized our understanding of space-time distortion, showing us that the universe is far more dynamic and interconnected than we ever imagined. It's a reminder that even the most abstract scientific theories can have profound, real-world implications, and that sometimes the universe speaks to us in ways we're only just beginning to understand. Have you ever wondered if time could flow differently for you compared to someone else? What if, in the blink of an eye, you could experience years while someone else ages only a few seconds? This isn't the premise of a sci-fi movie, it's the reality of time dilation, one of the most mind-bending predictions of Einstein's theory of relativity. Time dilation tells us that time isn't a universal constant. It's more like a river flowing at different speeds depending on where you are and how fast you're moving. And nowhere is this more vividly illustrated than in the famous twin paradox. Picture this: two identical twins born on the same day decide to part ways. One stays on Earth living a normal life while the other embarks on a journey through space at a speed close to the speed of light. Decades later, when the traveling twin returns, something extraordinary happens. The twin who stayed on Earth has aged significantly while the spacefaring twin appears much younger. How is this possible? According to Einstein's theory, time slows down for objects moving at extremely high speeds. This means that the faster you travel, the slower time passes for you relative to someone who isn't moving as quickly. It's a concept that challenges our everyday experience of time as something fixed and unchanging. But the twin paradox isn't just a thought experiment, it has real-world implications. Take GPS satellites, for example. These satellites orbit Earth at incredibly high speeds, and because of time dilation, the clocks on board actually run slightly faster than those on the ground. If scientists didn't account for this discrepancy, GPS systems would be off by several kilometers within minutes, rendering them useless for navigation. To keep everything accurate, engineers have to adjust the clocks on these satellites to compensate for the effects of both speed and gravity, another factor that influences time dilation. It's a perfect example of how a seemingly abstract concept like relativity has a direct impact on our daily lives. Gravity also plays a crucial role in this phenomenon. The stronger the gravitational field, the slower time moves. This means that if you were standing at the base of a mountain, time would pass ever so slightly slower for you compared to someone at the peak where gravity is weaker. It's an effect so subtle that you'd never notice it in everyday life, but it's there, quietly shaping the way time flows around us. Time dilation forces us to rethink what we know about the universe. It shows us that time isn't a rigid, unchanging force, but a flexible, dynamic dimension that can stretch and contract depending on the circumstances. Whether it's the twin paradox or the precise functioning of GPS satellites, time dilation reveals a universe far stranger and more intricate than we often imagine. It's a reminder that even the most familiar aspects of reality can hold surprises, waiting to be uncovered by those who dare to look closer. Now, let's turn our attention to a phenomenon that feels almost like the universe itself is spinning a cosmic web around massive objects. This is the realm of frame dragging, a subtle but profound effect where a rotating body, like a planet or black hole, twists the fabric of space-time around it. Imagine dropping a spinning top into a bowl of honey. As the top rotates, it pulls the honey around with it, creating a swirling pattern. Frame dragging works in a similar way, except instead of honey, it's the very fabric of space-time that gets dragged along by the rotation of a massive object. This effect, also known as the Lenz-Thirring effect, was first predicted by physicists Joseph Lenz and Hans Thirring in the early 20th century. They suggested that massive rotating objects don't just create gravity, they also twist the space-time around them like a spoon stirring a cup of tea. For decades, this idea remained a theoretical curiosity until scientists found a way to test it in the real world. One of the most famous experiments involved a satellite called Gravity Probe B, which carried ultra-precise gyroscopes into orbit around Earth. Over time, the gyroscopes detected tiny deviations in their orientation, caused by the subtle twisting of space-time due to Earth's rotation. It was a groundbreaking confirmation of a prediction made nearly a century earlier. But what does frame dragging mean for the objects around these massive rotating bodies? The effect is especially noticeable near black holes, where the rotation can be so extreme that it drags space-time along with it, creating a swirling vortex. Anything that gets too close, whether it's dust, gas, or even light, gets caught in this cosmic whirlpool, spiraling around the black hole like water circling a drain. This twisting of space-time can also influence the orbits of nearby stars and planets, subtly altering their paths in ways that wouldn't happen if the central object weren't rotating. Frame dragging doesn't just affect the motion of objects, it also provides a unique window into the nature of gravity itself. By studying how space-time twists around massive rotating bodies, scientists can test and refine our understanding of general relativity. It's a reminder that gravity isn't just a force that pulls objects together. It's a dynamic, shape-shifting phenomenon that interacts with mass, motion, and even time in ways we're still uncovering. This subtle yet profound aspect of space-time distortion reveals the intricate dance between mass, rotation, and the cosmos. It's a testament to how even the smallest effects can have far-reaching implications, reshaping our understanding of the universe one twist at a time. Whether it's a spinning planet or a whirling black hole, frame dragging shows us that space-time is far from static. It's a living, breathing fabric, constantly shaped and reshaped by the objects within it. And as we continue to study these effects, we uncover new layers of complexity, each one bringing us closer to understanding the true nature of gravity and the cosmos. What if the universe itself were alive, constantly growing and stretching in ways we can barely comprehend? This isn't just a poetic idea, it's the startling reality of our expanding universe. For decades, scientists believed the cosmos was static, a fixed backdrop of stars and galaxies. But in the late 1920s, astronomer Edwin Hubble made a discovery that shattered this notion. He found that galaxies are moving away from us, and the farther they are, the faster they're receding. This revelation led to the groundbreaking conclusion that the universe is expanding, and it's doing so at an accelerating rate. But what's driving this expansion? The answer lies in one of the greatest mysteries of modern physics: dark energy. Dark energy is an invisible, elusive force that permeates all of space, pushing galaxies apart and stretching the fabric of space-time itself. Think of it like a cosmic tug-of-war. On one side, gravity tries to pull everything together, while on the other, dark energy relentlessly pushes everything apart. And right now, dark energy is winning. This relentless expansion isn't just a subtle change, it's reshaping the universe on a colossal scale. Vast cosmic voids are forming between galaxies, regions so empty that they stretch for millions of light years. These voids are like the empty spaces in an ever-growing sponge, growing larger as the universe expands. But what does this mean for the future of the cosmos? One possibility is a scenario known as the Big Rip. In this dramatic endgame, the expansion of the universe becomes so rapid that it overcomes all forces holding matter together. Galaxies, stars, planets, and even atoms could be torn apart as space-time stretches to its limits. It's a chilling vision of the universe's ultimate fate, where the very fabric of reality is stretched so thin that it disintegrates entirely. While this scenario is still speculative, it highlights just how powerful and mysterious dark energy truly is. The discovery of dark energy has profound implications for our understanding of the universe. It challenges the idea that gravity is the dominant force on cosmic scales and raises questions about the nature of space-time itself. Why is the universe expanding faster and faster? What is dark energy exactly? These are questions that scientists are still grappling with, and they remind us that the cosmos is far more complex and enigmatic than we often assume. This accelerating expansion also changes how we think about the universe's evolution. In the distant future, galaxies will be so far apart that their light will no longer reach us, leaving the night sky eerily dark. Civilizations born billions of years from now might look up and see only their own galaxy, unaware of the vast cosmic tapestry that once surrounded them. It's a humbling thought, one that underscores the fleeting nature of our cosmic perspective. The expanding universe and dark energy invite us to rethink our place in the cosmos. They remind us that the universe is not a static stage but a dynamic, ever-changing entity, full of mysteries waiting to be unraveled. From the formation of cosmic voids to the potential for a big rip, these phenomena challenge our understanding of space, time, and the forces that shape our reality. As we continue to explore the universe's expansion, we're not just uncovering the secrets of dark energy, we're glimpsing the ultimate destiny of the cosmos itself. Now, let's venture into one of the most speculative yet captivating ideas in the realm of space-time distortion: cosmic strings. Picture the early universe, a seething cauldron of energy and matter, cooling rapidly after the Big Bang. As it cooled, the fabric of space-time itself may have developed cracks or defects, like the imperfections that form in ice as water freezes. These defects, if they exist, would take the form of cosmic strings, thread-like structures so thin they're almost one-dimensional, yet unimaginably dense, packing the mass of an entire star into a filament just a single atom wide. Cosmic strings are thought to stretch across the universe, forming vast, intricate webs that could span billions of light years. Unlike black holes or wormholes, which warp space-time into extreme curves, cosmic strings create a unique kind of distortion. Imagine running your finger along a taut rubber sheet. It would create a ripple, a slight fold in the material. Cosmic strings do something similar to space-time, bending it in ways that could produce extraordinary effects. For example, light passing near a cosmic string might split into two paths, creating a phenomenon called gravitational lensing, where a single object appears as multiple images in the sky. One of the most intriguing possibilities is that cosmic strings could have played a role in shaping the universe as we know it. In the chaotic aftermath of the Big Bang, these strings might have acted as gravitational seeds, pulling matter together and helping to form the first galaxies. In this way, they could be seen as cosmic architects, quietly influencing the structure of the cosmos from behind the scenes. Some scientists even speculate that cosmic strings might still exist today, remnants of the universe's fiery birth, lurking unseen in the vast emptiness of space. But what makes cosmic strings truly fascinating is their potential to serve as cosmic time capsules. Because they're thought to have formed in the earliest moments of the universe, they could carry information about conditions that existed long before stars or galaxies ever came into being. Studying them, if we ever find evidence of their existence, could give us a direct window into the universe's infancy, offering clues about how everything began and how it evolved into the cosmos we see today. Of course, cosmic strings remain purely theoretical for now. No direct evidence of their existence has been found, and detecting them would be incredibly challenging. Their thinness and the subtlety of their effects make them nearly invisible to our current instruments. Yet, the very idea of these space-time defects challenges our understanding of the universe, pushing us to think creatively about the nature of reality and the forces that shaped it. Whether they're real or not, cosmic strings remind us that the universe is full of mysteries waiting to be uncovered, and that sometimes the most extraordinary ideas are the ones that stretch our imaginations the furthest. What if the stars weren't as far away as they seem? What if we could bend the rules of the universe itself to travel faster than light, not by breaking the laws of physics, but by bending space-time to our will? This is the tantalizing idea behind the Alcubierre Drive, a theoretical concept that takes inspiration from science fiction and turns it into a scientifically grounded possibility. Proposed by physicist Miguel Alcubierre in 1994, this concept imagines a spacecraft that doesn't move through space but instead manipulates the fabric of space-time around it, creating a warp bubble that could propel the ship at speeds faster than light without ever technically breaking Einstein's cosmic speed limit. Here's how it works. Instead of the spacecraft traveling through space, the Alcubierre Drive would compress space-time in front of the ship and expand it behind, effectively creating a wave that carries the ship along. Picture a surfer riding a wave. They're not moving through the water. The wave itself is doing the work. In the same way, the Alcubierre Drive would surf on a warp bubble, allowing it to cover vast distances in a fraction of the time it would take using conventional propulsion. It's a concept that feels like it's straight out of Star Trek, but it's rooted in the mathematics of general relativity. However, there's a catch, and it's a big one. To create this warp bubble, the Alcubierre Drive would require something called exotic matter, a hypothetical substance with negative energy density. This isn't your everyday material. It's a form of matter that defies the usual rules of physics, possessing properties that allow it to counteract the positive energy of regular matter. The problem is, exotic matter has never been observed in nature, and creating it in a lab is currently beyond our capabilities. Without it, the warp bubble collapses, leaving the Alcubierre Drive in the realm of theory rather than practice. Despite this hurdle, the idea of faster-than-light travel through warp bubbles has captured the imagination of scientists and dreamers alike. It pushes the boundaries of what we think is possible, challenging us to rethink our understanding of space-time and energy. Could we one day find a way to harness exotic matter or discover an alternative method to create a warp bubble? The answer isn't clear, but the pursuit of this idea has already led to new insights into the nature of space and the limits of physics. The Alcubierre Drive also raises fascinating questions about the future of interstellar travel. If we could create a warp bubble, we might be able to visit distant stars and even other galaxies within a human lifetime. Imagine setting foot on a planet orbiting Proxima Centauri, our nearest stellar neighbor, or exploring the mysteries of a galaxy billions of light years away. The possibilities are as vast as the universe itself, but this concept isn't just about the distant future, it's also a reminder of how science fiction can inspire real scientific breakthroughs. The Alcubierre Drive shows us that the line between imagination and reality is often thinner than we think, and that the wildest ideas can sometimes lead to the most profound discoveries. Whether or not we ever build a warp-capable spacecraft, the pursuit of this dream challenges us to think bigger, dig deeper, and explore the universe with a sense of wonder and possibility. After all, the stars may be far, but with ideas like the Alcubierre Drive, they might not be out of reach forever. What if two particles could communicate instantly, no matter how far apart they are in the universe? This isn't science fiction, it's the bizarre reality of quantum entanglement, a phenomenon so strange that even Albert Einstein called it spooky action at a distance. Quantum entanglement occurs when two particles become linked in such a way that the state of one instantly influences the state of the other, regardless of the distance between them. It's as if they're connected by an invisible thread that transcends space and time, defying everything we know about classical physics. To understand just how strange this is, imagine flipping two coins simultaneously. In the classical world, the result of one coin toss has no effect on the other, they're independent events. But in the quantum realm, if two particles are entangled, measuring one instantly determines the state of the other, whether they're a millimeter apart or separated by billions of light years. This instantaneous connection seems to violate the speed limit of the universe, the speed of light, raising profound questions about the nature of space-time itself. Experiments have repeatedly confirmed the reality of quantum entanglement, leaving no doubt that this phenomenon is a fundamental feature of the universe. In one famous experiment, scientists sent entangled photons to two different locations, separated by over 1,000 kilometers. When they measured the properties of one photon, the other photon's properties instantly matched, as if they were communicating faster than light. This result baffled scientists because it suggests that information is somehow traveling instantaneously, something that classical physics says is impossible. But here's where things get even more mind-bending. Quantum entanglement doesn't just challenge our ideas about space and time. It forces us to reconsider whether space-time is as fundamental as we once thought. In classical physics, space-time is the stage on which everything happens a fixed, unchanging backdrop. But entanglement suggests that space-time might not be the ultimate framework of reality. Instead, it could be an emergent property, something that arises from deeper, more fundamental connections between particles. In other words, space-time might not be the foundation of the universe. It might be more like a surface effect, a byproduct of these entangled relationships. This idea has profound implications for our understanding of the cosmos. If space-time isn't fundamental, then what is? Some theories suggest that the true building blocks of reality are quantum fields or networks of entangled particles, with space-time emerging as a sort of illusion created by their interactions. This would mean that the universe operates on a level far deeper and more interconnected than we ever imagined, with entanglement serving as the glue that holds everything together. The challenge now is to reconcile this quantum view with our understanding of gravity and general relativity. While quantum mechanics excels at describing the behavior of particles on the smallest scales, general relativity explains the large-scale structure of the universe. But the two theories don't play nicely together, and entanglement sits right at the heart of this conflict. Solving this puzzle could unlock a unified theory of everything, a framework that explains both the quantum and cosmic realms in one cohesive picture. Quantum entanglement doesn't just challenge our understanding of space-time. It invites us to rethink the very nature of reality. It shows us that the universe is far more interconnected and mysterious than we ever imagined, with particles whispering to each other across vast distances in ways that defy explanation. As we continue to explore this phenomenon, we're not just uncovering the secrets of quantum mechanics, we're peering into the hidden fabric of the cosmos itself, unraveling the threads that tie it all together. And who knows, what we find might just rewrite the rules of reality as we know it. What if everything we see, touch, and experience in the universe is nothing more than a projection, a cosmic hologram? This might sound like the plot of a futuristic movie, but it's actually a serious theory in modern physics known as the Holographic Principle. At its core, this idea suggests that the three-dimensional world we perceive could be a kind of illusion, a projection of information encoded on a two-dimensional surface. Imagine the universe as a giant movie screen, with all the stars, galaxies, and even you as the audience being nothing more than a detailed projection of data stored on that flat surface. It's a concept that turns our understanding of reality on its head, and it all starts with black holes. The holographic principle first gained traction in the context of black hole physics. When matter falls into a black hole, it's lost to the outside universe, but what happens to the information it carries? According to the laws of quantum mechanics, information can never be destroyed, so this creates a paradox. In the 1970s, physicist Jacob Bekenstein proposed that black holes might store information about the matter they consume, not within their interiors but on their surfaces. This idea was expanded by Leonard Susskind and Gerard T. Hooft, who suggested that the entire universe might work the same way. In this view, space-time isn't the fundamental fabric of reality. It's a kind of hologram, a projection of information stored on a two-dimensional boundary. But how does this work in practice? Think of it like a 3D movie. When you watch a film in 3D, the images appear to have depth and texture, but they're actually encoded on a flat screen. The holographic principle suggests that the universe operates in a similar way. All the complexity and richness of the cosmos, from the swirling of galaxies to the beating of your heart, could be encoded on a two-dimensional surface, with our perception of three dimensions being a kind of cosmic illusion. This idea isn't just a wild speculation. It's rooted in the mathematics of string theory and quantum gravity, offering a potential bridge between the microscopic world of particles and the large-scale structure of the universe. One of the most compelling pieces of evidence for the holographic principle comes from black hole entropy. Entropy is a measure of disorder, and black holes have an enormous amount of it, so much that it seems to scale with their surface area, not their volume. This is strange because in most systems, entropy increases with volume. The fact that black holes seem to store information on their surfaces rather than within their interiors aligns perfectly with the holographic principle. It suggests that the true storage space of the universe might be two-dimensional, with our three-dimensional reality being a kind of projection or shadow. The implications of this idea are staggering. If the holographic principle is correct, it could provide a unified framework for physics, reconciling quantum mechanics and general relativity. It could also change how we think about space-time itself. Instead of being a fundamental entity, space-time might emerge from deeper, more abstract layers of reality, like a hologram emerging from a flat surface. This would mean that the universe is far more interconnected and information-driven than we ever imagined, with every event, every particle, and every force being part of a vast cosmic code. The holographic principle doesn't just challenge our understanding of the universe, it invites us to rethink the very nature of reality. It suggests that the cosmos might be more like a simulation or a projection than a physical, tangible entity. And while this idea is still speculative, it's a powerful reminder that the universe is far stranger and more complex than we can see with our eyes. As we continue to explore this radical theory, we're not just uncovering the secrets of black holes or the nature of space-time, we're peering into the very fabric of existence itself, unraveling the code that might hold the key to understanding everything. What if our universe is just one page in an infinite cosmic library, where every book tells a different story of reality? This is the mind-bending idea behind the multiverse theory, a concept that suggests our universe might be just one of countless others, each with its own unique set of physical laws and constants. Imagine a vast tapestry of realities, some eerily similar to ours, others so alien they defy comprehension. In this view, space-time isn't confined to a single universe. It stretches across an unimaginable expanse, connecting or perhaps even branching into parallel worlds. The multiverse theory isn't just a wild speculation. It emerges naturally from several areas of modern physics. One of the most compelling frameworks comes from quantum mechanics, where the concept of quantum superposition suggests that every possible outcome of an event actually happens, but in separate, parallel realities. Think of it like flipping a coin. In our universe, it lands on heads, but in another, it lands on tails. These branching paths create an ever-growing tree of possibilities, with each decision or random event spawning new universes. This is known as the many worlds interpretation, and it paints a picture of reality that's both infinite and endlessly diverse. But how does space-time play into this? In some multiverse models, space-time distortion could act as the bridge between these parallel realities. Wormholes, for example, might not just connect distant points in our universe. they could link entirely different universes, creating a cosmic network of interconnected worlds. Alternatively, the fabric of space-time itself could fold or stretch in ways that allow universes to coexist side by side, like sheets of paper stacked in a filing cabinet. The idea is as thrilling as it is speculative, but it raises profound questions about the nature of existence. Could we ever detect these other universes, or are they forever hidden from our view? The implications of the multiverse theory are staggering, both scientifically and philosophically. On the scientific front, it offers a potential explanation for some of the most puzzling aspects of our universe. Why, for instance, do the fundamental constants of nature, like the speed of light or the strength of gravity, have the precise values they do? If there are infinite universes, each with different constants, it's no surprise that we find ourselves in one where those values allow for stars, planets, and life to exist. This is known as the Anthropic Principle, and while it doesn't explain why our universe is the way it is, it provides a framework for understanding our place within a much larger cosmic landscape. Philosophically, the multiverse challenges our sense of uniqueness. If there are infinite versions of reality, does that make our lives less meaningful or more? Could there be versions of you living out every possible choice, every path not taken? These questions blur the line between science and metaphysics, inviting us to ponder the very nature of identity and existence. Yet, for all its allure, the multiverse theory remains just that, a theory. Observational evidence is elusive, and some critics argue that it's untestable by definition. But scientists are exploring creative ways to search for clues. Some look for imprints of other universes in the cosmic microwave background, the faint afterglow of the Big Bang. Others study the behavior of particles in high-energy physics experiments, searching for anomalies that might hint at interactions with parallel realities. While these efforts haven't yielded definitive proof, they keep the dream of the multiverse alive, pushing the boundaries of what we think is possible. The multiverse theory doesn't just expand our understanding of the cosmos, it stretches our imaginations to their limits. It invites us to consider a reality that's far grander and more complex than we ever dreamed, where every possibility plays out in its own unique universe. Whether or not we ever find proof of parallel worlds, the very idea challenges us to think bigger, to question our assumptions, and to marvel at the infinite possibilities hidden within the fabric of space-time. After all, in a multiverse, anything and everything might be possible. What if time itself could crystallize, forming structures that pulse and oscillate without ever losing energy? This isn't a futuristic fantasy, it's the reality of time crystals, a bizarre and groundbreaking discovery that has turned our understanding of matter and time on its head. Time crystals are a completely new phase of matter, one that defies the laws of traditional thermodynamics by exhibiting periodic motion even in their lowest energy state, known as the ground state. Unlike ordinary crystals, which have repeating patterns in space, time crystals repeat their patterns in time. They're like cosmic clockwork, ticking away in perfect rhythm forever. The concept of time crystals was first proposed by Nobel laureate Frank Wilczek in 2012. At the time, it seemed like a wild idea. After all, how could something move perpetually without an external energy source? According to classical physics, perpetual motion is impossible, as systems always tend toward equilibrium, losing energy over time. But time crystals flip this idea on its head. They exist in a state of non-equilibrium, meaning they're never truly at rest. Instead, they oscillate between different configurations, creating a stable, repeating pattern in time. This behavior is so strange that it challenges our most fundamental ideas about symmetry and the nature of time itself. One of the most fascinating aspects of time crystals is how they break time translation symmetry. In physics, symmetry is a powerful concept. It describes how certain properties of a system remain unchanged under specific transformations. For example, a snowflake looks the same if you rotate it by 60 degrees, and the laws of physics don't change if you shift them forward or backward in time. But time crystals disrupt this symmetry. Their oscillations occur at regular intervals, creating a pattern that repeats over time, even though the system itself doesn't gain or lose energy. It's as if time itself has been folded into a crystalline structure, with the crystal ticking like a clock that never winds down. So, how do time crystals work? The key lies in their quantum nature. Unlike classical systems which settle into equilibrium, quantum systems can remain in a state of constant flux, thanks to the strange rules of quantum mechanics. Time crystals are created by carefully manipulating quantum systems, such as chains of atoms or ions, to induce this perpetual motion. In experiments, scientists have used lasers and magnetic fields to kick these systems into a rhythmic state, causing them to oscillate indefinitely. It's a delicate dance, one that requires precise control over the quantum realm. But what makes time crystals truly exciting isn't just their strange behavior, it's their potential applications. One area where they could revolutionize technology is quantum computing. Quantum computers rely on the fragile states of quantum bits or qubits, which are easily disrupted by external noise. Time crystals, with their stable, repeating patterns, could provide a way to protect qubits from these disturbances, making quantum computers more robust and reliable. They could also serve as ultra-precise clocks, far more accurate than anything we have today, thanks to their perfect, unending rhythm. Beyond their practical uses, time crystals also raise profound questions about the nature of time itself. If time can crystallize, what does that say about its fundamental properties? Could time be more malleable, more dynamic than we've ever imagined? These questions push the boundaries of physics, challenging us to rethink some of our most deeply held assumptions about the universe. Time crystals are a reminder that the universe is full of surprises, even in the most familiar realms of physics. They show us that matter can take on forms we never thought possible, and that time itself might hold secrets we're only beginning to uncover. As we continue to explore this strange new phase of matter, we're not just advancing science, we're peering into the very heart of reality, uncovering the hidden rhythms that might underpin the cosmos itself. And who knows, what we find might just change the way we see time forever. What if I told you that even the emptiest corners of the universe are far from empty? That even in the void of space, where there's seemingly nothing at all, there's a hidden world of activity, energy, and forces at play. This is the bizarre reality revealed by the Casimir Effect, a phenomenon so strange that it challenges our very understanding of what it means for space to be empty. At its core, the Casimir Effect shows us that the vacuum of space isn't just a blank slate. It's a seething, dynamic arena where quantum fluctuations create forces that can pull objects together, even in the absence of any traditional energy source. The effect was first predicted by Dutch physicist Hendrik Casimir in 1948, and it works like this. Imagine placing two uncharged metal plates extremely close together in a vacuum. According to classical physics, nothing should happen. There's no charge, no gravity, no obvious force at play. But in the quantum world, something extraordinary occurs. The space between the plates becomes a stage for quantum fluctuations, tiny ripples of energy that constantly pop in and out of existence. These fluctuations are a hallmark of quantum mechanics, a reminder that even in a vacuum, space is never truly empty. It's filled with a kind of quantum foam of particles and energy. Here's where it gets even stranger. Outside the plates, these quantum fluctuations can take on any wavelength, but between the plates, they're restricted by the narrow gap. This creates an imbalance in energy, with more fluctuations pressing on the plates from the outside than from within. The result, the plates are subtly pushed together as if drawn by an invisible hand. It's a force so small that it's only noticeable at microscopic scales, but its implications are enormous. The Casimir effect shows us that even the vacuum of space is alive with energy, a concept that has profound implications for our understanding of space-time and the universe itself. But what does this mean for space-time distortion? If the vacuum isn't truly empty, then what we think of as nothing is actually a rich, dynamic field of energy. This energy, often referred to as vacuum energy or zero-point energy, could play a key role in shaping the fabric of space-time. Some theories suggest that vacuum energy might even contribute to the expansion of the universe, acting as a kind of cosmic fuel that drives galaxies apart. It's a tantalizing idea, one that connects the microscopic world of quantum fluctuations to the grand structure of the cosmos. The Casimir effect also opens up fascinating possibilities for future technologies. If we could somehow harness vacuum energy, it could revolutionize everything from energy production to space travel. Imagine spacecraft powered not by traditional fuel but by the boundless energy of the vacuum itself. While this remains speculative, the idea is grounded in real science, and researchers are already exploring ways to manipulate these quantum forces. For example, scientists are experimenting with materials and structures that could amplify or control the Casimir effect, potentially paving the way for new technologies that tap into the hidden energy of empty space. This phenomenon doesn't just challenge our understanding of physics, it invites us to rethink what we know about reality. The Casimir effect shows us that the universe is far more dynamic and interconnected than it appears, with even the emptiest spaces teeming with activity. It's a reminder that the cosmos is full of mysteries waiting to be uncovered, and that sometimes the most profound discoveries come from asking simple questions: what's really in the void? And how can we unlock its secrets? As we continue to explore the implications of the Casimir effect, we're not just uncovering the strange properties of vacuum energy, we're peering into the hidden layers of the universe itself. And who knows, what we find might just change the way we see space, time, and the very nature of reality. After all, in a universe where even nothing is something, the possibilities are truly endless. What if the reason we haven't found alien civilizations isn't because they don't exist, but because they've figured out how to bend the rules of space-time itself? This is one of the most tantalizing ideas tied to the Fermi paradox, a question that has puzzled scientists and dreamers alike for decades. Named after physicist Enrico Fermi, the paradox asks a simple yet profound question. If the universe is so vast and filled with billions of stars and planets, why haven't we encountered any signs of intelligent life? One possible answer might lie in the strange and mind-bending nature of space-time distortion phenomena that could allow advanced civilizations to move, hide, or exist in ways we can't yet comprehend. Consider this: an alien civilization far more advanced than ours might have mastered technologies that manipulate space-time, such as wormholes or warp drives. These technologies could allow them to traverse the cosmos in ways that bypass the limitations of light speed, making interstellar travel not just possible but routine. Imagine a society that has unlocked the secrets of wormholes, creating shortcuts through the fabric of space-time to visit distant galaxies without the need for centuries-long journeys. For them, the vastness of the universe might not be a barrier but a playground, with space-time serving as their highway. But here's where it gets even more intriguing. If these civilizations have such advanced capabilities, they might also have the ability to manipulate space-time to remain hidden from us. Think about it. If you could fold space-time like a piece of paper, you could create regions that are effectively invisible or unreachable to those who haven't figured out the same tricks. They could exist right alongside us in parallel dimensions or within folded pockets of space-time, completely undetectable by our current technology. It's like living next door to someone who's mastered the art of invisibility. You might never know they're there, even if they're just a step away. Another possibility is that these civilizations have moved beyond physical existence as we understand it. If they've harnessed space-time to its fullest potential, they might have transcended the need for physical bodies or traditional forms of communication. Instead of building starships or sending radio signals, they could exist as energy-based beings or even as information encoded in the fabric of space-time itself. In this scenario, the Fermi paradox isn't about the absence of alien life. It's about the gap between their form of existence and our ability to perceive it. Of course, these ideas remain speculative, but they highlight just how much we still have to learn about space-time and its potential. The Fermi paradox doesn't just challenge us to search for extraterrestrial life, it pushes us to rethink the very nature of the universe and the possibilities hidden within its fabric. Could the answers to this cosmic riddle lie in the quirks of space-time? Could alien civilizations be all around us, hidden in plain sight, waiting for us to catch up? As we continue to explore the mysteries of space-time distortion, we're not just uncovering the secrets of the cosmos, we're opening doors to possibilities that stretch far beyond our current understanding. Whether it's through wormholes, advanced propulsion, or entirely new forms of existence, the Fermi paradox reminds us that the universe is full of surprises. And who knows, the day we crack the code of space-time might just be the day we finally meet our cosmic neighbors. Until then, the search continues, fueled by curiosity, imagination, and the timeless question, are we truly alone? Let's rewind the cosmic clock to the very beginning, the moment when space and time themselves were born. The Big Bang isn't just the origin of the universe as we know it, it's the birth of space-time, the stage upon which all of existence unfolds. But here's the question that keeps physicists up at night. What happened before the Big Bang? Was there a before at all? The answer isn't straightforward, and it leads us into some of the most fascinating and speculative realms of modern physics. One of the leading theories about the early universe is inflationary cosmology, which suggests that the universe underwent an exponential expansion in the first fraction of a second after the Big Bang. Picture a balloon inflating faster than the speed of light, stretching space-time itself in the process. This rapid expansion wasn't just a random event, it was driven by a mysterious force known as the inflaton field. As space-time stretched, it smoothed out irregularities, creating the remarkably uniform cosmic microwave background we observe today. But it also left behind tiny quantum fluctuations, seeds that would eventually grow into the galaxies, stars, and planets we see around us. In this way, space-time distortion wasn't just a consequence of the Big Bang. It was the very mechanism that shaped the universe. But what about the moments before inflation? This is where things get truly mind-bending. Some theories propose that the Big Bang wasn't the absolute beginning, but rather a transition from a previous state of existence. For example, the idea of a quantum bounce suggests that our universe could have emerged from the collapse of a previous one, like a cosmic phoenix rising from the ashes. In this scenario, space-time didn't begin at the Big Bang. It was reborn, carrying traces of its earlier form into the new universe. Another possibility is that our universe is just one bubble in a vast multiverse, where countless other universes are constantly being born, each with its own unique properties and laws of physics. These ideas push the boundaries of our understanding, hinting at a reality far more complex and interconnected than we ever imagined. Quantum gravity, a field that seeks to unify quantum mechanics and general relativity, offers another perspective. According to some models, space-time itself might emerge from a more fundamental layer of reality, like a tapestry woven from quantum threads. In this view, the Big Bang wasn't the beginning of space-time, but the moment when it crystallized into the structure we recognize today. It's a radical idea, one that challenges our conventional notions of time and existence. Could space-time be an emergent property, something that arises from deeper, more fundamental interactions? If so, then the Big Bang might not be the ultimate origin. It could just be a milestone in a much larger cosmic story. The role of space-time distortion in the early universe goes beyond just expansion. It also played a critical role in the formation of cosmic structures. Those tiny quantum fluctuations, stretched and amplified by inflation, became the gravitational seeds that pulled matter together, forming the first galaxies and stars. Without those distortions, the universe might have remained a featureless void, devoid of the rich complexity we see today. In a sense, space-time distortion isn't just a quirk of the cosmos, it's the reason we exist at all. This journey back to the beginning isn't just about understanding the Big Bang, it's about uncovering the fundamental nature of reality itself. From inflationary cosmology to quantum gravity, these theories offer glimpses into a universe that's far stranger and more dynamic than we ever imagined. They remind us that the cosmos is full of mysteries, from the tiniest quantum fluctuations to the grandest cosmic structures. And as we continue to explore these ideas, we're not just uncovering the secrets of the universe, we're discovering the story of our own origins. After all, every atom in your body, every star in the sky, and every moment in time can be traced back to that singular, explosive moment when space-time itself was born. And who knows, what we find might just change the way we see everything. Why does time always seem to move forward? Why do we remember the past but not the future? These questions lie at the heart of one of the most fundamental mysteries of the universe, the arrow of time. Unlike space, where we can move freely in any direction, time appears to flow in only one way, from past to future. But what gives time this direction? The answer lies in a concept that might sound familiar: entropy, the measure of disorder in a system. And when we bring space-time distortion into the mix, things get even more intriguing. Entropy is governed by the second law of thermodynamics, which states that in an isolated system, disorder always increases over time. Think of a cup of coffee cooling down or an ice cube melting. These are everyday examples of entropy at work. But here's where it gets fascinating. The increase of entropy is what gives time its arrow. It's the reason we experience time as a one-way street, always moving from a state of lower entropy ordered to higher entropy disorder. Without this tendency toward disorder, time wouldn't have a clear direction, and the past and future would blur together. Now, let's add space-time distortion to the equation. In regions of extreme gravity, like near black holes or in the early universe, space-time can become so warped that it challenges our understanding of time's flow. For example, near a black hole's event horizon, time slows down dramatically due to gravitational time dilation. But could space-time distortion ever reverse the arrow of time? Could entropy somehow decrease, allowing time to flow backward? Theoretically, it's possible, but only under conditions so extreme that they defy our current understanding of physics. One idea that emerges from general relativity is the concept of closed time-like curves, paths through space-time that loop back on themselves, effectively creating a time loop. If such curves exist, they could allow for time travel, at least in theory. Imagine a spacecraft following one of these curves. It would leave the present, travel into the future or past, and eventually return to its starting point. But here's the catch. Closed time-like curves create paradoxes like the famous grandfather paradox, where traveling back in time to prevent your own birth would create a logical contradiction. These paradoxes suggest that while the math might allow for time loops, the universe might have built-in safeguards to prevent them. The relationship between space-time distortion and entropy also raises questions about the nature of the universe itself. Some theories propose that the arrow of time might not be universal. In a multiverse scenario, for instance, different universes could have different arrows of time, with some moving forward and others moving backward. It's a mind-bending idea, one that challenges our everyday experience of time as a linear, one-directional flow. At the heart of this discussion is a deeper truth. Time isn't just a backdrop for the universe, it's an active participant, shaped by the interplay of entropy, gravity, and space-time distortion. The arrow of time, as we know it, is a product of these forces working together to create the universe we inhabit. And while the idea of reversing time or creating closed time-like curves remains speculative, it forces us to rethink what we know about the nature of existence. This peculiar aspect of space-time distortion doesn't just challenge our understanding of time, it invites us to see the universe in a new light. It shows us that even the most familiar concepts, like the flow of time, can hold profound mysteries waiting to be uncovered. Whether it's through the lens of entropy, the paradoxes of time travel, or the possibility of alternate arrows of time, the arrow of time reminds us that the universe is far stranger and more dynamic than we often imagine. And as we continue to explore these ideas, we're not just uncovering the secrets of time, we're unraveling the very fabric of reality itself. What if the universe is held together by an invisible hand, a force so powerful that it shapes galaxies, yet so elusive that we can't even see it? This is the mystery of dark matter, a substance that makes up roughly 85% of the universe's mass but remains completely invisible to our eyes. Unlike stars, planets, or even black holes, dark matter doesn't emit, absorb, or reflect light. It's entirely transparent, yet its presence is undeniable. How? Because it bends space-time itself, leaving behind gravitational fingerprints that reveal its existence. The story of dark matter begins with a simple observation: galaxies rotate faster than they should. According to the laws of gravity, the outer stars in a galaxy should move more slowly than those near the center, much like planets farther from the sun orbit more slowly than those closer in. But when astronomers measured the speeds of stars in distant galaxies, they found something startling. The outer stars were moving too fast, so fast that the galaxies should have torn themselves apart. The only explanation: there had to be more mass in these galaxies than we could see, mass exerting a gravitational pull strong enough to hold everything together. That unseen mass is dark matter, but dark matter doesn't just hold galaxies together, it shapes the very structure of the cosmos. Imagine space-time as a vast, invisible fabric. When you place a heavy object on that fabric, like a bowling ball, it creates a depression, warping the surface around it. Dark matter does the same thing, but on a cosmic scale. Its immense mass distorts space-time, creating gravitational wells that guide the formation of galaxies and galaxy clusters. Without dark matter, the universe would look very different, perhaps even too sparse and disorganized for life to exist. The search for dark matter is one of the most exciting frontiers in modern science. Astronomers have mapped its distribution across the universe by observing how its gravitational pull bends the light from distant galaxies, a phenomenon known as gravitational lensing. These cosmic distortions act like a magnifying glass, revealing the hidden presence of dark matter even though we can't see it directly. But what is dark matter made of? That's the million-dollar question. One leading theory suggests it's composed of weakly interacting massive particles, or WIMP, hypothetical particles that rarely interact with ordinary matter but exert gravitational effects. Scientists are conducting experiments deep underground, shielded from cosmic radiation, hoping to detect these elusive particles as they pass through Earth. Another possibility is that dark matter isn't made of particles at all, but is instead a manifestation of space-time itself. Some theories propose that dark matter could be linked to anomalies in the fabric of space-time, such as microscopic black holes or cosmic strings. These structures, if they exist, could explain the gravitational effects we attribute to dark matter while offering new insights into the nature of space-time. It's a tantalizing idea, one that blurs the line between matter and the fundamental structure of the universe. Yet, despite decades of research, dark matter remains one of the greatest unsolved mysteries in physics. Its invisible presence challenges our understanding of the cosmos, forcing us to rethink what we know about matter, gravity, and the very fabric of reality. Each new discovery brings us closer to unraveling its secrets, but the journey is far from over. What we do know is this: dark matter is the hidden architect of the universe, the unseen force that shapes galaxies, bends light, and holds the cosmos together. As we continue to explore the mysteries of dark matter, we're not just uncovering the secrets of the universe, we're rewriting the story of existence itself. What we find might not only explain the invisible forces shaping our reality, but also reveal new dimensions of space-time we never knew existed, and who knows? The day we finally detect dark matter could be the day we unlock the next great chapter in our understanding of the cosmos. Until then, the search continues, a testament to humanity's endless curiosity and our drive to uncover the hidden truths of the universe. What happens to information that falls into a black hole? At first glance, it might seem like a straightforward question, but the answer has sparked one of the most heated debates in modern physics. This is the heart of the black hole information paradox, a puzzle that pits two of our most successful scientific theories, quantum mechanics and general relativity, against each other. And at the center of this debate lies a startling possibility: that space-time itself might break down at the edge of a black hole, creating something known as a firewall. Let's start with the basics. According to quantum mechanics, information can never be destroyed. It's a fundamental principle of the universe, like a cosmic rulebook that says every bit of information must be preserved, no matter what. But when something falls into a black hole, it crosses the event horizon, the point of no return. General relativity tells us that once inside, it's crushed into the singularity, a point of infinite density where the laws of physics as we know them cease to exist. So, what happens to the information about that object? Does it vanish, breaking the rules of quantum mechanics? Or is it somehow preserved, defying what we know about black holes? This is where the paradox begins. If information is lost in a black hole, quantum mechanics is fundamentally wrong. But if it's preserved, where does it go? One proposed solution is the firewall hypothesis, a radical idea that suggests the event horizon isn't the smooth, uneventful boundary we once thought. Instead, it could be a seething wall of energy, a fiery barrier that destroys anything crossing it. Think of it like hitting a brick wall at the speed of light, an instant, violent end that vaporizes matter and scrambles information beyond recognition. The firewall hypothesis is as controversial as it is fascinating. On one hand, it offers a way to preserve quantum mechanics by destroying information at the event horizon, preventing it from ever reaching the singularity. On the other hand, it directly contradicts general relativity, which predicts that crossing the event horizon should be uneventful, a smooth transition into the black hole's interior. This creates a stark divide. Either quantum mechanics is incomplete, or our understanding of space-time at the event horizon is fundamentally flawed. The implications of this paradox are profound. If firewalls exist, they could mean that space-time itself breaks down at the edge of a black hole, shattering our current models of the universe. It would force us to rethink not just black holes, but the very nature of space-time and how it interacts with quantum mechanics. Some physicists have even suggested that resolving this paradox could be the key to unifying these two theories, creating a theory of everything that explains the universe at every scale. But the debate is far from settled. Critics of the firewall hypothesis argue that it's too extreme, a band-aid solution that doesn't address the deeper issues at play. Others propose alternative ideas like holography, which suggests that information falling into a black hole isn't lost but instead encoded on its surface like a cosmic hard drive. This idea ties back to the holographic principle we explored earlier, offering a way to preserve information without breaking the laws of physics. The black hole information paradox doesn't just challenge our understanding of black holes, it forces us to confront the limits of our knowledge. It's a reminder that even the most well-established theories can have cracks, and that the universe is full of mysteries waiting to be unraveled. Whether firewalls exist or not, this paradox has already reshaped how we think about space-time, gravity, and the quantum realm. And as scientists continue to grapple with these questions, one thing is certain: the answers will change the way we see the cosmos and our place within it. What if everything around you, every star, every galaxy, even the very fabric of space-time, is nothing more than lines of code in an unimaginably vast computer simulation? This is the essence of the simulation hypothesis, a theory that's equal parts mind-bending and provocative. At its core, the idea suggests that our universe might not be the fundamental reality we assume it to be. Instead, it could be a highly advanced simulation created by some form of intelligence far beyond our understanding. And while this might sound like the plot of a sci-fi movie, it's a serious concept that has garnered attention from philosophers, scientists, and tech innovators alike. But how does this idea connect to space-time distortion? And what would it mean if our reality were indeed a simulation? Let's start with the basics. If the universe is a simulation, then space-time itself would be a construct, a kind of software program running on cosmic hardware. In this view, the distortions we observe in space-time, like gravitational lensing or the warping effects near black holes, could be seen as glitches or intentional features of the code. Think of it like a video game. When you move through a virtual world, the environment responds in real time, adjusting to your actions. Similarly, in a simulated universe, space-time might render itself dynamically, creating the illusion of a seamless, continuous reality. But what happens when the simulation encounters an error? Could we detect signs of pixelation or glitches in the cosmic code? One intriguing possibility is that the smallest units of space-time, Planck length and Planck time, might represent the pixel size of the simulation. These are the tiniest measurable scales in physics, beyond which our current understanding breaks down. If the universe is a simulation, these scales could be the equivalent of the pixels on your screen, the fundamental building blocks of reality. And just as a video game can sometimes show artifacts or glitches when pushed to its limits, the universe might reveal similar anomalies under extreme conditions. For instance, some scientists have speculated that high-energy cosmic rays could interact with the quantum foam of space-time in ways that expose the underlying code, offering glimpses into the simulation's architecture. But the simulation hypothesis isn't just about the mechanics of space-time. It also raises profound philosophical questions. If we're living in a simulation, who created it? Are we the result of an experiment, or are we simply characters in someone else's virtual world? And perhaps most unsettling, if the simulation were to end, would we even know? These questions challenge our understanding of existence, forcing us to confront the nature of reality itself. Are we the players or are we the game? From a scientific perspective, the simulation hypothesis pushes us to rethink our assumptions about the universe. If space-time is a construct, then the laws of physics might not be immutable truths but rather programmed rules, subject to change or manipulation. This opens up wild possibilities, like the idea that advanced civilizations within the simulation could hack the code, altering the fabric of reality to suit their needs. Imagine being able to rewrite the laws of gravity or create wormholes at will. It's a level of control that would make even the most advanced technologies seem primitive by comparison. Yet, for all its fascination, the simulation hypothesis remains just that, a hypothesis. There's no direct evidence to prove or disprove it, and many scientists argue that it's untestable by definition. But that hasn't stopped researchers from exploring creative ways to search for clues. Some have proposed that if the universe is a simulation, it might exhibit subtle anomalies like patterns in cosmic background radiation or irregularities in particle behavior that betray its digital nature. Others suggest that advanced civilizations within the simulation might leave behind signatures in the form of mathematical constants or encoded messages waiting to be discovered. Whether or not the simulation hypothesis holds water, it serves as a powerful reminder of how little we truly know about the universe. It challenges us to think beyond the boundaries of conventional science and consider possibilities that once seemed unimaginable. And if nothing else, it sparks a sense of wonder and curiosity, inviting us to question the nature of reality and our place within it. After all, if the universe is a simulation, then every discovery we make, every mystery we unravel, brings us one step closer to understanding the code that holds it all together. And who knows, the day we crack that code might just be the day we discover the true nature of existence itself. What if space-time, the very stage on which the universe unfolds, isn't smooth and continuous but instead a chaotic, frothy sea at its smallest scales? This is the startling idea behind quantum foam, a concept that takes us to the very edge of our understanding of reality. Imagine zooming in on the fabric of space-time so closely that it no longer resembles the smooth, flowing surface we're used to. Instead, it becomes a turbulent, ever-changing foam where tiny bubbles of space-time constantly pop in and out of existence. These fluctuations are so small and fleeting that they're almost impossible to detect, yet they could hold the key to understanding the ultimate nature of the universe. The concept of quantum foam arises from the clash between two of the most successful theories in physics, quantum mechanics and general relativity. Quantum mechanics governs the behavior of the smallest particles, describing a world of probabilities and uncertainties. General relativity, on the other hand, explains the large-scale structure of the universe, where space-time is a smooth, continuous fabric shaped by gravity. But when we try to combine these two theories, things break down. At incredibly small scales, smaller than a trillionth of the width of an atom, the smoothness of space-time gives way to a chaotic, fluctuating foam. It's as if the universe itself is pixelated, with each pixel representing a tiny, unstable bubble of space-time. This idea isn't just a speculative thought experiment, it's grounded in some of the most advanced theories in physics. Take loop quantum gravity, for example. This theory suggests that space-time isn't continuous but made up of tiny, discrete loops like the threads of a cosmic tapestry. These loops weave together to form the fabric of the universe, but at the smallest scales, they create a frothy, quantum foam. It's a radical departure from the smooth space-time of general relativity, but it offers a potential way to reconcile the quantum and cosmic worlds. String theory, another leading candidate for a theory of everything, takes a different approach. Instead of loops, it proposes that the fundamental building blocks of the universe are tiny, vibrating strings. These strings exist in a higher dimensional space, and their vibrations give rise to particles, forces, and even space-time itself. In this framework, quantum foam could be seen as the result of these strings interacting in complex, unpredictable ways, creating a fluctuating, foam-like structure at the tiniest scales. But what does this mean for the ultimate nature of space-time? If quantum foam exists, it suggests that space-time isn't fundamental but emergent, a byproduct of deeper, more fundamental processes. This idea challenges our most basic assumptions about reality. Instead of space-time being the backdrop for the universe, it could be something that arises from the interactions of quantum particles or strings. It's a shift in perspective that forces us to rethink not just space-time, but the very nature of existence. The implications of quantum foam extend far beyond theoretical physics. If space-time is fundamentally fuzzy at small scales, it could have profound effects on our understanding of black holes, the Big Bang, and even the arrow of time. For example, near the singularity of a black hole where gravity becomes infinitely strong, the smoothness of space-time might break down entirely, replaced by a chaotic quantum foam. Similarly, in the earliest moments of the universe, space-time might have been so frothy and unstable that it defies our current understanding of physics. Exploring quantum foam takes us to the cutting edge of science, where the boundaries between the known and the unknown blur. It's a reminder that the universe is far stranger and more complex than we often imagine, and that even the most fundamental aspects of reality can hold surprises. Whether through loop quantum gravity, string theory, or some yet-to-be-discovered framework, the quest to understand quantum foam is a journey into the heart of the cosmos itself. And as we continue to unravel its mysteries, we're not just uncovering the secrets of space-time, we're discovering the hidden layers of reality that shape everything we know. From the crushing depths of black holes to the frothy chaos of quantum foam, the universe has shown us that space-time is anything but ordinary. What began as a simple exploration of 20 peculiar aspects of space-time distortion has unfolded into a breathtaking journey through the very fabric of reality. Each discovery, from gravitational waves to cosmic strings, has revealed a cosmos that defies our expectations, challenging us to rethink what we thought we knew about existence itself. These phenomena aren't just scientific curiosities, they're gateways to understanding the universe on a deeper level. They remind us that the cosmos is full of mysteries waiting to be uncovered, and that every question we answer leads to even more fascinating puzzles. Whether it's the mind-bending nature of wormholes or the invisible presence of dark matter, these discoveries push the boundaries of human knowledge, inspiring us to dream bigger and explore further. As we continue to study space-time distortion, we're not just learning about the universe, we're learning about ourselves. Each breakthrough brings us closer to understanding our place in the grand cosmic tapestry, connecting us to the stars, the galaxies, and the very forces that shape reality. The journey is far from over, and the possibilities are endless. Who knows what secrets still lie hidden in the folds of space-time, waiting for us to uncover them. Thank you for joining us on this extraordinary adventure through the wonders of the cosmos. If you enjoyed this journey, don't forget to like, subscribe, and share your thoughts in the comments below. Let us know which aspect of space-time distortion fascinated you the most. Until next time, keep looking up, keep asking questions, and keep exploring the infinite mysteries of the universe. The stars are calling, and the journey is just beginning.